Hi everyone, my name is Paul Tasker and I am a fourth year pharmaceutical and industrial chemistry student here in the University of Limerick, and I will be presenting my presentation, which is on the removal of valuable metals from aqueous solutions using adsorption. To look then at the relevance of the project, so metals, and in particular heavy metals, are quite toxic in low or trace quantities. There's an economic incentive for recycling these metals. For example, in e-waste in 2019, approximately $57 billion worth of metal was sent to landfill. Within this e-waste then, you have higher concentrations of metals than would be present in the natural metal ores. For example, with gold, there's 40 times greater concentrations of gold in e-scrap than there is in their respective ores. Central research questions to this project then: how do metals enter the aqueous solutions? Where do they come from? Where do they go? How can we remove them from aqueous systems? And then how can we recover the metals after we've removed them? Looking at issues to do with recycling then. So metals rarely exist as pure fine substances. In e-waste, they're normally in complex heterogeneous mixtures, so with polymers like fiberglass and plastics. The metals themselves then might also be pure, or they might be alloyed. Looking then at the efficiency of extraction versus recovery. So extraction is typically quite easy. You can just use some acid and it'll dissolve the metal. But recovering all of the metal from that acid is rarely 100% efficient. And as the concentrations go lower, you have a lower economic incentive to recover the metals. So you result in basically trace amounts of these metals getting thrown out and entering aqueous systems then. Adsorption is the process by which species known as adsorbates adhere onto solid surfaces known as adsorbents. It's typically cheap and easy to implement. There's no requirement for energy, and it's also suitable for low adsorbate concentrations. Adsorption can occur through physical or chemical interactions, whether it's physisorption or chemisorption. In this project, there's a primary focus on chemisorption, in particular electrostatic adsorption, which relies on the electronegativity differences between your active sites, which I've circled here in red. Advantages and disadvantages then of adsorption. So it's easy to use, it's cheap, it's quite easy to regenerate your adsorbent, or rather remove your adsorbate from the active sites. It's easily optimized, it's quite flexible through modification to the overall adsorbent structure, and you can also have selectivity and sensitivity in your materials. However, as there is no energy requirement, you typically have to have quite a long contact time. Depending on the system parameters, you can have stability issues, so be they thermal, mechanical, or pH. Your active sites typically degrade based on how you regenerate your adsorbents, and then often you might actually require modification for adsorption to be effective. The experimental methodology began with selecting metals and adsorbents, which were identified through literature reviews. Selected adsorbents were chitosan, cellulose, and biochar. And these are selected based on the criteria of being cheap, easy to modify, regenerable, being natural, abundant, stable, and selective. And copper was selected as a metal for its presence in real-world scenarios. Nickel was selected based on its toxicity, and silver was selected based on its economic value. The overall objectives of the project then. So initially, we wanted to identify metals suitable for removal. We want to identify porous supports that were capable of removing these metals. Then was the overall actual removal of the metals from aqueous solutions. Optimization of the adsorption parameters, or how we conducted the overall process. Gain experience in using inorganic quantitative and qualitative analytical methods, and then identification of future progression, be it through regeneration of the material or through modification of our adsorbents. There were two main analytical methods used throughout this project. So Ftir, or Fourier transform infrared spectroscopy, was used to identify functional groups on our adsorbents, and this was based on the absorbance or transmittance of infrared light at characteristic wavelengths, which then gave information about functional groups present. The concentration of metals before and after adsorption was analysed using atomic absorption spectroscopy, which looks at the absorption of light by free gaseous metal ions according to Beer's law, which gave a linear relationship between absorbance and concentration values. Here you can see the Ftir spectrum obtained for chicken biochar. Chicken biochar is typically quite a complex structure, and that results in a complex Ftir spectrum, as you can see from the lack of resolution of these peaks. But there are a few peaks that you can identify, which I've circled here in red, and I've just given a brief rundown of what these peaks correspond to in terms of functional groups on the right there. You can see that the Ftir spectrum of cellulose is far better resolved compared to biochar, and this is because it's a much simpler overall chemical structure. There are a few main peaks that you can identify here. You can see a peak at 1000 wave numbers, which is carbon to oxygen bonds, and there's another quite broad peak at about 3300 wave numbers, which corresponds to hydroxyl groups. Chitosan has a very similar Ftir spectrum to cellulose, and that's because they have very similar overall chemical structures. However, the main difference is in the peak around 3300 wave numbers. You can see it's more broad in this spectrum, and that's because both the amine groups and the hydroxyl groups absorb in this wave number region. The first main experiment was conducted to identify which adsorbents had the most affinities for which adsorbates. And you can see here, 1 refers to chitosan, 2 refers to biochar, and 3 refers to cellulose. You can see biochar was very, very good at removing silver from solutions. Chitosan was quite good at removing both silver and copper from solutions, but cellulose, however, was quite poor at adsorbing all of the metals that we tested, so you can say that then cellulose requires some modification for it to be effective. After that then, we looked at optimizing time or contact time. So again, we used 50 milligrams of our adsorbents, so chitosan and biochar, and this was added to 50 ml of our metal solutions. It was maintained at 25 degrees C and stirred at 190 RPM. And you can see that the majority of your adsorption has happened by the 60-minute mark. If you extended the process onto 120 minutes, you didn't really get too much more adsorption happening, so 60 minutes of contact time was deemed to be most effective. We then conducted some adsorption isotherms. This looked at essentially saturating our adsorbents material to identify the maximum adsorbent loading of biochar with silver and chitosan with copper. You can see from these graphs, the top one is to do with biochar. That achieved about 84 milligrams of silver per gram of biochar, and chitosan then was capable of absorbing about 58 milligrams of copper per gram of chitosan. And then once we had identified that there was full loading, identified by kind of a straightening out of these graphs, we then fitted various adsorption isotherm models, as will be covered later. So the first model that we fitted was the Langmuir model. That states that only a monolayer of our adsorbate forms on the adsorbents. Each of the active sites have the same, essentially, energy and size distribution, and there's no interactions between adsorbed molecules. And you can see from our straight lines that we have a very, very good R-squared value, which states that essentially the assumptions made by Langmuir in this model fit very, very well to this process. We also fitted the Freundlich model, but however you can see that the R-squared values were not as high as the Langmuir model, so it appears that the Langmuir model is still the most effective at governing what this process was doing. Same again then for the Temkin model. Again, you can see we have quite a good R-squared value, but again, these are not as high as the Langmuir model, so we can then conclude that the Langmuir model is the most effective model at governing the overall adsorption process. Another parameter that we optimized throughout this project was the pH of the system. So pH is a measure of the free protons that exist in solution, which can then have effect on the ionization of our active sites. So you can see that we varied the pH from about 6 to about 1. Chitosan was most effective at adsorbing at around pH 6 and about pH 1, but for reasons you'll see later, the results at about pH 1 are actually invalid. Biochar then was most effective at adsorbing at around a pH of 3. The last set of experiments then was looking at the competition of metals for active sites, or competitive metal adsorption. So to do this, we made a series of single metal solutions, binary metal solutions, and then ternary metal solutions. And you can see the overall effect of having co-ions or ionic competition for the active sites in this graph here. So key findings then, as I mentioned in the pH optimization section, chitosan was actually soluble at the low pH, which means that the adsorption results at that pH were actually invalid. Chitosan would turn blue after adsorption with copper, and that can be partially as a result of copper forming amine complexes, which is characterized by that kind of royal blue color you can see in the bottom left picture. Cellulose, as it was quite poor throughout the experiment, needs modification for it to be a useful adsorbent. The overall adsorption process of biochar with silver and chitosan with copper was governed by the Langmuir model. In terms of competition for active sites, biochar would preferentially absorb silver over copper, and the presence of nickel actually increased the absorption of silver. In terms of chitosan then, the presence of nickel actually increased the silver absorption, and you can see as well that silver was directly competing with copper for those active sites. So where can we go from here then? So we can begin to look at the modification of these materials, in particular cellulose, be they modification of all of the functional groups or only some of the functional groups. Greater characterization of biochar, simply because biochar is just such a complex structure, so maybe some TEM or SEM images of the material could be quite useful. Transitioning then towards maybe flow column testing rather than batch processing could be quite useful. And then also the suspension of our adsorbents in microgels or microbeads could be quite interesting, as you can actually increase stability through doing so. Finally then, I'd just like to say a massive thank you for listening to my project. I really appreciate it. And if you have any questions about this, feel free to email me at the email I provided at the start.